Okay, so we have talked about how to solve a very basic linear equation. In this video, we're going to move on to what is probably the second easiest type of equation to solve, and that is a very basic radical equation. Before we get started, I do want to say one thing about radical equations. First of all, as soon as I say that name, you should recognize what these equations are going to look like based on the words in that name, right? So equation just means I'm going to have two things that are equal to each other. So there's going to be an equal sign. And radical just means one of those things is going to have a radical in it. For our class, it will usually be a square root. That's the type of radical we will usually work with. And in our class, only one of the two sides will have a square root. Okay, so when I say we're working with basic radical equations, that's what I mean by that. We're working with square roots usually, and only one of them. We might, in our class later, maybe we'll see how things go this year, move into some more advanced radical equations where perhaps there's more than just one radical. There might be two square roots or something like that. And then we also might run into problems where it's not a square root, but maybe it's a cubed root or a fourth root or something like that too. So, but in this video, we're focusing on just the basics. All right. So with that said, let's go ahead and look at our learning objectives and we'll get started here today. So our learning objectives are be able to solve a basic radical equation. I started writing in involving square roots, but I canceled that out. I think with what we're going to talk about today, we might be able to handle more than just square roots, although ultimately square roots are definitely our objective. Okay, so I would say for sure, make sure you're comfortable with square roots. But in this video, I'm going to talk a little bit more than just square roots. And then specifically, if it is a square root, you need to recognize when the equation might not have a solution. And we did not deal with this with linear equations. We didn't talk about the potential of an equation not having a solution because linear equations, unless there's something really weird and funky going on, linear equations always have solutions. But that's not true with radicals. And so that's one of the things we're going to talk about in this video. All right, so here we go. The first thing I want to do is start with just a very quick review of what we did with linear equations. So if I had 2x, you know what, I'm going to change, well, let's do this for a second. 2x plus 4 equals 6. Let's say that I've got that. 2x plus 4 equals 6, okay? Now I'm going to change this for a second. I want this to not just be an x, right? Variables can represent lots of different things. So to emphasize the fact that this variable is anything that we don't know, I'm not just going to call it X, I'm going to call it an A, for it's anything. It's anything that we don't know. Now, we usually traditionally do an X, but that doesn't change the way we do algebra if it's not an X. Anytime it's something that we don't know, we do the same basic idea to figure out what it is. In this case, if you want to pause the video and solve this to figure out what that anything might be, you should be capable of doing that. So go ahead and give it a try. All right, so hopefully you've figured out that that anything is a 1, but let's take a look at how we can know that for sure. We know that we're going to get this anything all by itself. We know we're going to work far away to close, so we're going to get rid of the 4 before we get rid of the 2. And we know we have to use inverse operations. So the inverse of adding 4 would be subtracting 4. That's going to make this 4 cancel out and go away. But we also know that anything I do to one side of the equation, I have to turn around and do it to the other side of the equation too. So it's like there's this, you know, some of your teachers probably have even done this. If we just imagine this, you know, the equal sign as being this division or this divider between the two halves of the problems, we need to keep the two halves equal. So we do things on both sides. Okay. Now, when I subtract the 4 on this side, these will just cancel each other out, and that's going to leave me with 2 times that unknown anything. And on this side, I've got 6 minus 4, which is equal to 2, and these are still equal to each other because I did that to both sides. So now I move on to the next thing I need to get rid of. I need to get rid of this 2. And because this is 2 times anything that I don't know, the way I get rid of multiplying by 2, the inverse of multiplying, is dividing. So now I'm going to divide both sides by 2. When I divide both sides by 2, these will cancel each other out. And now I've got the unknown anything all by itself, it's still equal to something. Notice that equal sign just keeps dropping down. And 2 divided by 2 is a 1. So anytime I have 2 times something plus 4, and the answer is going to be 6, this thing is always going to be a 1. Okay, that's what we've just proven, okay, in this process. So we can talk about solving for x, but really I want to kind of make a slight mental shift to make this bigger than I'm just solving for x. Really what we're saying is anytime 2 times something plus 4 equals 6, that something is always going to be a 1. That something is always going to equal to 1. Always. Anytime there's 2 times something plus 4 that's equal to 6. Now, why am I making this, what seems like a non-point, such a big point, right? I mean, that's pretty subtle, talking about an unknown variable versus anything that we don't know. That's pretty subtle. So what are you doing? Why are we doing something that's like that? Well, this moves us into our radical equations. So think about this. We just said 2 times anything plus 4 equals 6. We did a bunch of algebra and we showed that anything is going to be equal to 1. That's what we just got done doing here, right? That's all the stuff that we just did on this paper. Okay, we just showed that. So now, this is what we did yesterday. Now what we're going to say is we're going to have 2 times something plus 4 equals 6. And so as soon as I write that, we know that something is going to be a 1. That's what we just proved. But my 1 is going to be a radical. So let's say that it's the square root of x plus 5. The square root of x plus 5. Okay. Now, the idea here is if I can get this thing all by itself, then I can get rid of the square root and I can figure out what x plus 5 is. In other words, I can use an inverse operator on the square root. But before I can use the inverse operator on the square root, I have to have the square root by itself. I have to know what the square root is equal to. All right. So the way I get the square root by itself so that I can use the inverse, the way that I figure out what this is equal to is exactly the same as the way I get anything by itself. I go through an identical algebra process that starts far away from that thing that I don't know and works its way in closer. Okay, so really what I have is I've got a scenario where this is the anything that I don't know. And if I want to get that thing by itself, what I would do to begin with is I would move this 4 to the other side. Okay, cancel that 4 out. These are gone. This is going to be 6 minus 4 is going to be 2, right? We know what this is because we just did it. And that leaves me with 2 times the thing that I don't know. 2 times that thing that I don't know. Okay. Now, if I want to get this thing that I don't know by itself, the next thing I need to do is get rid of this 2. So I'm going to divide both sides by 2. That makes these go away. I've got this equal 2 divided by 2 is a 1. And so that exact same process that we used up here, I'm using the identical process. So it's no surprise what I end up with is anything that I don't know. If I multiply by 2 and add 4 and the answer turns out to be 6, then that thing must have been a 1. So that process is identical, right? Now, this then brings us to the new part. I need something that will make a square root go away. I need an inverse operator for square roots, okay? So this might be a good time to start sort of summarizing the inverse operator. Operator, inverse operator. Okay, so what we've used up to this point is we've figured out if I have a plus sign, the minus sign is what cancels it out. And the other way around is true also. If I have a minus sign, the plus sign is what cancels it out. Okay, so that's what we did up here. To get rid of this 4, it was a plus 4, so I used a minus 4. Okay, so we know that. We know that if there's a multiplication problem, it's division that cancels that out. And so here I had 2 times something, so I divided. But the other way around also works. If I have a division problem, multiplication will cancel that out. Okay, now, if you think back to last week, we just got done working with fractions, right? Rational expressions. So somewhere down the road in the future, we're going to want to solve rational expressions. So how will I get rid of division? I'll use multiplication. Okay, now that's coming in the future. That's not today. Today, we've got the square root sign. So if I have the square root sign, do we know what cancels out square roots? Okay. Well, square roots are asking the question, what times itself equals this thing? So obviously it has something to do with multiplying things times themselves. So what's the fancy math word for multiplying something by itself? It's the square. The square is what undoes square roots, okay? So if I have the square root of x, then x squared, that's how I do the inverse, okay? I'm going to square both sides. That's what I'm going to do. And of course, it turns out that the other way around is true. If I have something being squared and I want to get rid of that square, I'll use the square root to do that, okay? That'll come later in our class also. That's not something for today. In fact, there's some weird stuff that happens here, so weird that some mathematicians wouldn't actually even call this an inverse. They would call it something else, but that's for another day. Let's get back to this problem. I have an x plus 5. There's a square root around it. I need to get rid of this square root. So the thing that makes square roots go away are squares, okay? Now, this is where things are a little bit weird. There's lots of numbers that I can add. I could do plus 4, I could do plus 12, I could do plus 73, I could do plus pi, I could do plus negative 2. There's lots of numbers you can add. So when I do my minus, I have to make sure my numbers match, minus 4. Okay, if this was a plus 5, I have to do minus 5. If this was plus 73, I have to do minus 73. But with square roots, that's not true. Square roots always are canceled out with squares. So we don't need anything extra. To cancel out this square root right here, I'm just going to square it. That's all I'm going to do. And squares and square roots, they cancel each other out. So this and this, they cancel. Okay, and they cancel each other, which means there's nothing left to impact the x plus 5. The x plus 5 is still there, completely untouched, unfazed. Nothing got to it. It's like, you know, this square is coming in, it's trying to get to the x plus 5, the square root jumps in its way, the two of them battle to the death, they're both gone, but the x plus 5 then just walks away because untouched, the square never made it there, the square root saved him, all right? So it's like the square root is his bodyguard or something, sacrificing its life to keep the x plus 5 untouched. And there it sits, untouched. But not just because it's untouched, that doesn't mean nothing else is impacted, right? Because we know if you square one side, you have to square the other side also. So that x plus 5 is going to be equal to, what does 1 times 1 equal? It equals 1. So x plus 5 is equal to 1. Now I need to get this x by itself. And now it's exactly the same as what we did yesterday. Again, to get x by itself, I'm going to have to subtract 5. And then I am done. And then I'm done. Okay, so this is the basic idea of how we solve problems with square roots. All right, let's write this process down in some steps. Let's proceduralize this process. Let's see if I can I get this to show up on the screen and my other piece of paper too. There we go. I think I got it. Okay, so here's what we just did there. All right, so steps for solving square root equations. Steps for solving square root equations. Number 1, the first thing we did is we got the square root all by itself equal to a number. Okay, now realize that that's a process, right? That wasn't done in one step. It took us several steps for us to get there. In this particular problem, it took 2 steps. There might be other problems where it takes more than 2 steps. There might be problems where it takes less than 2 steps. But we went through this whole process from the beginning until we got right here, where we got this thing all by itself, and we just did it like normal, regular algebra. I saw there was a +4, so -4, boom, boom, boom. I saw there was a multiply by 2, so divide by 2, boom, boom, boom. Okay, so get the square root. I hope you're okay if I'm abbreviating square root like that, okay? Get the square root by itself equal to a number, okay? In fact, if you think about what we talked about in yesterday's notes, we said when you get something by itself equal to a number, what you're doing is you're solving. So you could say this, simply solve for the square root, AKA solve for the square root. Okay, so that's the vocabulary that we learned in the last video. When you get a variable by itself equal to a number, you're solving for that variable. Here, we're getting the square root by itself equal to the number, so we're solving for the square root. So that's our first step. Once we did that, we got rid of the square root using its inverse, and the inverse is a square. All right, so that's our next step. Use inverse to get rid of the radical. Okay, now in the land of square roots, we could say that a little easier, AKA square both sides. Okay, but this might be a good place to just pause for a second and think about bigger picture. What if it wasn't a square root? All right, so I said our focus right now in our class is square roots, but what if, just what if, don't go back and change the problem, right? But just look at this for a second. What if instead of being a square root, what if it was a cubed root instead? Well, cube root asks the question, what times itself 3 times equals blah, blah, blah. Okay, so if I want to cancel out something that's multiplying by itself 3 times, I'm going to use a cube. Okay, what if it was the 13th root? Then I would raise it to the 13th power. Okay, so with radicals, it's pretty simple to know what power to raise it to. It's whatever your index is, whatever root you're taking. So when we're doing square roots, remember that's one of those odd times in math where our ninja is not a 1. When we're doing square roots, the ninja is a 2. So when we do square roots, because the ninja is a 2, we're going to raise it to 2 on both sides. Okay, but if it's not, then we'll go from there. Okay, so once we do that, the radical's gone. That leaves us with a nice linear equation, and then that's how we finish, is we solve the remaining linear equation. Okay, now at this point in our class, it's going to always be linear. That's not a rule for math. It's not like it just has to be linear. There's no exceptions. It's going to always be linear. Okay, if we get to the point in our class where we're doing some more advanced radical equations, we might end up having to solve something that's not linear when we get to this spot. But right now in our class, it's going to always be linear. All right, and so those are our steps. Those are our steps. All right. Now, there is one last thing I want to mention in this video. There will be a second video that has some examples, so you can watch those examples if you want to. But there's one last kind of theory piece that goes to this video. All right, something that you need to know. For reasons that we're not going to necessarily talk about right now, although you can always ask me and I'll be glad to talk with you about this. Anytime you take a square root in mathematics, this is just the nature of square roots. It's the way mathematicians have defined square roots. It brings up this concept called a principal root, if you wanted to do a Google search and see what's going on here or something like that. But anytime we do square roots in mathematics, the answer is always a positive number. Okay, so if I ask you to take the square root of 9, the answer is always positive 3. It's never negative 3. Even though we know that negative 3 times negative 3 equals 9, we always write positive 3, always. If we say take the square root of 81, we always say it's positive 9. If you don't believe me, grab your calculator, take the square root of 81 600 times, and see if it doesn't give you positive 9 all 600 times. It's going to. It's never going to change. The square root is always positive. This is a concept called the principal root. that we don't really learn that concept in our class, but it's something you need to be aware of. Why do I need to be aware of that? Because if we ever run into a problem where we're taking the square root of something we don't know, and the problem claims that the answer should be negative, that cannot happen. So because you can never get a negative answer, anytime we see this in a problem, then we say that the problem has no solution. The problem has no solution, okay? The way square roots have been defined, square roots can't have negative answers. And so if you get a situation where it says the square root is a negative number, you can stop right there. Remember, when do we get the square root all by itself equal to a number? We do that in step 1. So if we finish step 1 and it's equal to a negative, we can stop. We don't have to go any further. There's no reason to finish. The answer is negative. In fact, I'm going to go back up here to our procedure, and I'm going to add that as a little note right here, as a little note right here. Note, okay, when we finish step 1 and we end up with the square root equal to a negative, if we finish step 1 and we end up with the square root equal to a negative, then there is no solution. And again, I'm abbreviating. I have to, that's okay. SOLN, abbreviation for solution there. SOLN for solution. Okay. And so we can stop as soon as we finish step 1 if it's equal to a negative. All right. Now, that's it for the theory and concepts, right? Going back to our learning objectives, solve basic radical equations. There's our procedure, 3-step procedure to solve a basic radical equation. And know when a square root does not have a solution. Notice that this is square roots, okay? What I just said is not true for every single radical. There are some radicals where it could be equal to a negative, but not square roots. Square roots do not ever equal negatives. So when does a square root not have a solution? If you get it all by itself and it's equal to a negative, there's not a solution. All right, so there is a second video that I'm going to post right after this with some examples. If you want to see examples of something that doesn't have a solution, or if you just need to see more examples of how to go through this process to solve, then make sure you watch that second video. But that's it for this one. Have a good one. Oh, and thank you for watching.